Hello, everybody. We're back. So trying something different. I'm not in my garage this time. I'm in my kitchen, although you can't see that. All you can see is what I write. So today we're going to talk about chapter 8 on external direct products. Chapter 8, external direct products, whatever those are. So I'm writing with my finger. Try not to judge me too hard. We're all doing what we can, right? So anyway, this is the motivation for external direct products is sort of thinking about if we have a group, what are the essential parts of a group, or what are the atoms? Is there a way to either make new groups from existing groups, or classify groups or factor them into fundamental parts the same way that integers can, right? So recall that the fundamental theorem of algebra is that all integers can be factored into prime factors. Those prime factors are the fundamental parts. All integers have a prime factorization. So essentially, prime numbers are the fundamental parts of an integer. Fundamental. Okay, so is there something that's similar to that for groups? Remember that we talked about group theory as being the algebraic abstraction of the idea of addition of integers. So let's take that further and say, well, what about the prime factorization, or the fundamental theorem of algebra? How does that transfer? Okay, so first we need a way to get new groups from existing groups. So that is the external direct product, or one of the ways. One is the internal direct product, and this one is the external direct product. In the case of abelian groups, they're one and the same. So anyway, we're going to first talk about external direct product. Sometimes called actually the direct sum. So we're going to let G1 and G2 be finite groups. Well, you can do this for any collection of groups. Oh, they don't have to be finite. Why make a... There's no difference in the definition. What am I doing? Okay. Let G and G2 be any group. My bad. Okay. Then the external direct product of G1 and G2 is denoted by G and then this funny O plus thing. So G external direct product G2, G1 direct sum G2 often is exactly the set of ordered pairs. A is in G1 and B is in G2. Okay? And you say, well, is that a group? Well, yeah, we're going to sort of define it to be a group by creating a multiplication or operation that definitely satisfies the group axioms. So with A, B dot multiplication, let's just make that a little bigger. Can I make it? No, not working. There we go. AB dot, still trying to use this thing, okay. AB dot CD is just AC BD. Okay, so we've got component-wise multiplication. And I don't think that we need to worry too much about whether this satisfies the group axioms, but it does. Okay, so the identity, well, let's see, G1 is, oh wait, we can't use G1, can we? First group axiom is it, gosh, that's awful, okay. First, forget it. The first group axiom is the multiplication associative, and it definitely is because it's associative in each component. So, you know, first group axiom I think you will believe me if I just say, well, it works, okay? The identity, what's that? it's the identity. Oh, let's use. Use the identity in G1, the first component, identity in G2, second component. So G1, G2, okay, and inverses, well, it's pretty clear that this is, check there, A inverse, B inverse. Okay. So all the group axioms work out. So here's an example. Three. Okay. For example, take Z2 direct sum Z2. Okay. I've actually used this notation before, but this is the set of all ordered pairs where the entries are from 0 and 1. And the multiplication is addition modulo 2. You can easily see that it's closed and associative and satisfies all that stuff. We know this is a group, okay? Then what about the plane? Okay, R2. Well, that's as a group, not a ring. That's just our direct sum R, our external direct product R. You know, ordered pairs, where you add them component-wise, add the vectors component-wise. So any vector space is an external direct product of real numbers, right? So these are ordered n tuples, A1, A2, all the way up to AN, right? You can think of those as vectors. So this notation here is just saying if you can do it for, you can take the internal direct product of 2 and you can do it for any number, right, by induction. So this is external direct product of n copies of R. Okay? All right. So what I'm going to end this video on, so we're not going to get done with the whole thing, but I do want to get to something interesting. So we're going to do a cool example. We're going to classify all groups of order 6. It doesn't have to be abelian. So if the order of a group is 6, then either G is isomorphic to the cyclic group with 6 entries, or the dihedral group with 6 elements. Okay, how do we prove that? So by Lagrange's theorem, the only possible orders of elements is 1, 2, 3, or 6, right? Element is in G. Then the order of the elements is 2, 3, or 6, or the element itself is the identity, right? There's only one element with order 1, so don't have to worry about that. Let's just not think of A as being the identity, okay? 'Cause that's silly. All groups have the identity. All right, so on the one hand, if there is some element with order 6, then we know that G is isomorphic to the cyclic group, right? Since G is actually equal to the group generated by A. Okay, so it's cyclic. All right, so we can assume that there are only, so now assume only non-identity elements have order 2 or 3. Okay, so if there's an element A, right, in G, oops, with order of A is 2, and B in G with order of B is 3, then G is actually equal to these 6 elements. Okay, reason for that is because oh, I forgot B squared. A, B squared. This is the only way we can have A and B in a group with only 6 elements and still be closed. Okay, notice that A inverse is A, B inverse is B squared, okay, and both have then the same order as their inverses, right? Okay, so there are 2 cases. Case 1, G is abelian. All right. We can show that then A, B has order 6. oops, G. AB is order 6. Come on. So I'm just going to leave that to you to show it, right? So remember, abelian means that AB is equal to BA, and we can show that any of the elements listed above, right, any of these ones here can be some multiple of or some power of A times B, because of the way the orders of A and B are. All right, so we know that's a contradiction because we assumed there aren't any elements of order 6. So we can't do that here. Okay. So case 2, it's not abelian. Okay. And in that case, we know that BAB, since it's closed, since the group is closed, must be in set A. Well, can't be the identity, because if it were, then AB would be equal to B inverse. Well, okay, let's just go over the cases for some of these. All right, so notice that AB is equal to AB squared if and only if B is equal to B squared. Okay, that's by cancellation. We also can't have A B squared equal to A, then that would mean B squared would be the identity. Can't have A B squared be B. So why not? Well, then this would mean that A would be equal to B squared, but the orders are different, right? So those are all contradictions too. Can't have any of those. All right. So what can BAB be? We know that it is not the identity, because then oh well, let's check that actually. This would mean that AB is equal to B squared, since B squared is the inverse of B, right? But we just showed, oh, we didn't show that. Okay, so then this is if and only if what is it? A is equal to B, right? But we know that's not true. They have different orders. All right. So what's last? What I want to show is that BAB is equal to um, B. Is that right? Or is that the only choice left? Let's see. So well, okay. Let's see. How about that? So that would mean that B is equal to, no, it's supposed to be, okay, hold on. What do I want it to be equal to? B A is not equal to A B, right? Because it's not abelian. So, but what if I had, so that would mean that A is not equal to B squared AB. Yeah, so what if we had A is equal to B, AB? Would that be possible? That means that B inverse A is equal to AB. Yes. And is that possible? Yes, it's actually the only possibility, right? So in other words, G is equal to the group generated by two elements, A, B, so that A squared equals B cubed equals the identity, and the one we just did here, oops, and a space. And B inverse A is equal to AB. And if you look at what that is, if you wrote out the Cayley table, that is exactly the dihedral group. Okay. The only other case, I guess, would be as if there were no elements of order 3 or no elements of order 4. This is not possible by just a counting argument. Maybe I'll save that for next time. Okay, I've got to finish up this video. As always, if you have questions, about the video, you can send them to me in an email and using the D2L email app, or you can put them in the comments in the discussion forums. Okay.